Okay, so these notes are going to be our class's review of functions. Now, we're not covering everything that you've learned in Algebra 1, Algebra 2, and Pre-Calc about functions. This is going to be a very brief review, and I'm going to split this review into two different parts. So this video will be part 1 of our functions review, and we're going to be looking at the definition of a function, representations of functions, function notation, domain and range, intercepts, and common functions. So this we're going to talk about in part 1. And then composite functions and piecewise defined functions we're going to discuss in part 2. So before we define a function, let's look at the definition of what a relation is. And when you see the word relation, you're probably also thinking of the word relationship. So a relation is a correspondence between two sets where each element in the first set, called the domain, corresponds to at least one element in the second set, called the range. So we're talking about sets of numbers. And I've drawn a picture here. So I have two circles, and each of these circles is meant to represent set of numbers. So the first set I'm naming the domain, and that's going to be, you could think about it as all of the input values, usually associated with the variable x. And then the range would be the set of numbers that would represent all of the output values. So the input values are values from the domain, and then they map to the output values that are in the range. And if each element from the domain maps to at least one element in the range, then we have a relationship between these two sets of numbers, or a relation. Okay, so let's continue with this picture. So I'm going to put some numbers. How about just like 1, 2, 3, and 4. So those values belong to the first set of numbers, the domain. And I'm going to throw some other numbers into the range. I'll use a different color. How about 5, 6, 7? Okay. So to show the relation, so I'm going to start with the number 1 that is an element of the domain. Let's say that the number 1 ends up mapping to the number 5. And let's say the number 1 also ends up mapping to the number 7. Okay, so our input of 1 ends up mapping to the number 5 as well as the number 7. And then let's say the number 2 belonging to the domain ends up mapping to 7 as well. And how about number 4 from the domain maps to number 6 as well as number 5. And then let's say the number 3 maps to the number 6. Okay, so this would represent a relation because each element in the domain, and the elements are the numbers 1, 2, 3, 4 in this picture, each of those elements ends up mapping to at least one element in the range. Some of them map to more than one, but they at least map to one. So the definition of a function is very similar to the definition of a relation. So a function is a correspondence between two sets where each element in the first set, called the domain, corresponds to exactly one element in the second set, called the range. So this term right here is the difference and is what defines a function. So let's use our picture. So let's say we have those same elements. So 1, 2, 3, 4. And then I think I was using purple. I think I used 5, 6, and 7. in my range. Okay, so for this picture to represent a function, each element belonging to the domain must map to exactly one element in the range. Okay, so let's say that 1 still maps to 5, but only 5. 2, how about 2 maps to 6? And how about the number 3 will also map to 6? That's okay. The input of 2 maps to exactly one element in the range, which that element is 6. And then the number 3, which is an element in the domain, maps to exactly one element in the range. That's fine. And then let's say 4 maps to 7. So each element in the domain ends up mapping to exactly one element in the range. So this picture would represent a function. So this is kind of helpful to think about. All functions are relations. However, not all relations are functions. And that's really important to remember. So there's different representations of functions and that you guys should be familiar with. So they can be represented numerically in some sort of a chart, kind of like the picture I just drew, or a table of values, graphically, verbally, like you can describe a function in words, and then algebraically with a mathematical model or an equation. So we're going to look at we're going to focus on a couple of these different representations. We're going to first talk about functions that are defined by equations. So typically a function represented by an equation uses the variables x and y. They're just the most common variables to use because we usually then want to graph equations in the xy plane, or where we usually refer to that horizontal axis as x and the vertical axis as y, but we could also use different letters to represent the input and output variables. X can be any number in the domain and is referred to as the independent variable. And then y, which depends on the value of x, is referred to as the dependent variable because y depends on x. X can be any value within the domain, and we'll talk about domain in a couple of minutes, but y, then the value of y depends on what the value of x is. And we say that y is a function of x, if that's true. If every value of x corresponds to exactly one value of y, then y is a function of x. Always think back to that definition. So not all equations define functions. Okay, so some equations end up just being relations. And then some equations end up actually representing functions. And let's go over how we can tell. So these two equations here look very similar, and you've probably seen both of these equations before. Well, let's pick a value for x. So why don't we let x equal to, how about 4? Okay, in this first equation, y equals to x squared, if we substitute 4 in for x and simplify, we would end up with y being equal to 16. And that would tell us that the point 4, 16 would lie on the graph of y equals to x squared. So a point on that graph would be 4, 16. If we were to let x equal to 4 over in this other equation, x equals to y squared, okay, to find the values of y, we would need to take the square root of both sides of the equation. And when we do that, we would get that y, or you could just look at this equation and solve by inspection for the values of y. You can look at this equation and go, okay, well, y has to be either positive or negative 2. So we end up with that input of 4, we end up with 2 different values for y, right? We end up with positive 2 and negative 2. So that means that there are actually 2 points that lie on the graph of x equals to y squared that have an x coordinate equal to 4. So we would have the point 4, 2 and the point 4, negative 2. Well, thinking back to the definition of a function, that's not a function, right? Our input of 4 belongs to the domain, ends up corresponding to 2 different output values, 2 different y values. So let me switch to red. This equation does not represent a function. It represents a relation because there's a relationship between 4 and 2 and negative 2. However, it does not represent a function. This first equation did represent a function, though. Because the input of 4 had exactly 1 output, 16. Okay, so usually, actually always, if you can solve for y explicitly, so you can have y written in terms of x, so y equals to some expression in terms of x, then that equation is going to represent a function. If we went back to this equation here and we solve for y, we would have y equals to plus or minus the square root of x, which plus or minus, that represents 2 different expressions there. So this would actually be the 2 equations. So y equals to the positive square root of x as well as y equals to the negative square root of x. And let's next talk about what that looks like graphically. Freeze it a little bit. Okay, here we go. All right, so next we're talking about functions represented graphically. So functions can be graphed in the Cartesian plane or the xy plane. And for a graph to represent a function, it must pass the vertical line test. So the vertical line test says, given a graph, if any vertical line that can be drawn intersects the graph in no more than 1 point, then the graph defines y as a function of x. And that just goes back to the definition of a function where every element in the domain must correspond to exactly 1 element in the range. Every x needs to map to exactly 1 y. Okay, so going back to these equations, okay, y equals to x squared. You guys are familiar with that graph. It's just the parabola. So let me quickly sketch that. All right, kind of the U-shaped graph that opens up. And then remember, for this equation, if we solved for y, remember how we ended up with y equals to plus or minus the square root of x, the 2 different equations? So if you wanted to graph that in your calculator, you would end up needing to type in 2 equations into 2 separate lines. Actually, let me move that up. Okay, so y equals to the square root of x, the positive square root of x, would be this graph. And then y equals to the negative square root of the y equals to the negative square root of x would look like that. And we end up with our sideways parabola. Okay, so we already said that this first equation represented a function. And looking at this graph, if we were to draw any vertical line, and there are infinitely many vertical lines that you could draw, any of those vertical lines would intersect the graph at exactly one point. So it would pass, this graph passes the vertical line test. Okay, however, the sideways parabola, the graph of x equals to y squared, let's think about when we inputted 4, we ended up with the two outputs for y. We had the point 4, 2, and then the point 4, -2. Sorry, I missed the negative. So if I were to draw a vertical line there, notice that the graph ends up intersecting that vertical line at 2 points, which means it fails the vertical line test, and x ends up corresponding to 2 different y's. So the vertical line test fails. Therefore, again, we've shown that this is not a function. It is a relation, but not a function. There's a relationship between x and y, but it fails the definition of a function. Okay, you guys should be familiar with your function notation. Function notation is a way that when we're dealing with multiple functions that we can name the function to stay organized, especially if you're trying to graph multiple functions or you're dealing with a bunch of different equations, or especially this year whenever we're wanting to take the derivative of a function. It helps us to stay organized. Function notation also allows us to see what value we're inputting into the function. So what value we're inputting into the independent variable, or x. F of x is probably the most common function name, but really most any letter could be used. And then it's also important to remember that different cases represent different functions. So like if you have a function named lowercase f and there's another function named uppercase f, those do not represent the same functions. So if I, in a quiz or a test, have named a function something, you need to continue with that name and using that case. You cannot switch. Just going back here, so we graph functions in the xy plane in ordered pairs. We use to represent points on the graph. Ordered pairs are x, y, or if you wanted to think of it as in terms of function notation, would be x, f of x. Right? F of x represents the output value. Let me see anything else to point out. Yeah, so y and f of x are interchangeable. Oh, big one. F of x does not mean f times x. It is function notation and not multiplication. All right, so let's practice using function notation. So with this function, f of x equals to x squared. If we wanted to find f of 2, that means we want to find the y coordinate that goes with x equals to 2. So basically what 2 maps to in the range. So to do that, f of 2 will be equal to, use parentheses to substitute values in so you don't make any sign errors. So 2 squared plus 2, and then we can simplify. So that would be 4 plus 2 equals 6. So we now know that the point 2, 6 would lie on the graph of f of x. Okay, and then if we want to find f of -1, we want to find the y-coordinate that goes with x equal to -1. Again, make sure you use the parentheses when you substitute in. That ends up being 1 plus 2. Oh, why did I write 3? I was getting ahead of myself. 1 plus 2, which is 3. So another point that lies on the graph of f would be the point -1, 3. Okay, C here is asking a different question. So it's saying find x such that f of x equals to 16. So we were solving for, or we were trying to determine what the y-coordinate was for a given x-coordinate. And now we want to find an x-coordinate or coordinates for a given y-coordinate. So what we can do is replace in our equation, we're going to replace f of x with 16. So we'll have 16 equals to x squared plus 2. And then we can subtract 2 from each side of the equation. And now we can take the square root, so use square root method to solve this quadratic equation. So we'll get x equals to plus or minus the square root of 14. 14 does not have any perfect square factors, so it cannot be simplified. So we actually ended up with 2 solutions here. We have x equals to the positive square root of 14, as well as x equals to the negative square root of 14. So that tells us that there are actually 2 points on the graph of f that have a y-coordinate equal to 16. And if you think about what that graph looks like, you know that should make sense. So the points that we would know would be the square root of 14, 16, and negative square root of 14, 16. So 2 different points. Okay, we can also evaluate functions for expressions. And you'll see us doing this with limits, and specifically when we are using the limit definition to find a derivative. So just looking ahead a little bit. Okay, so if we want to evaluate the function f for x plus 1, we're going to replace x with x plus 1. Make sure you use parentheses. If you don't have the parentheses, it's incorrect. And this complicated little expression, you will become very familiar with. It's something called the difference quotient. And we will talk more about the difference quotient very soon. Okay, so this is f of x plus h. So the function f evaluated at x plus h minus the function f all divided by h. So that would be x plus h squared plus 2. So that's the first piece there. So it's just this piece. Minus the function and f. So I'm going to use brackets, or you could use any grouping symbol. So minus x squared plus 2, because you're subtracting the whole function. So that would be this part right here. And then all divided by h. And we could simplify that. We could distribute the negative. We could multiply the x plus h squared out. Let's do that. So in the numerator, we'll have x squared plus 2xh plus h squared plus 2. And then when we distribute that negative, we'll have negative minus x squared minus 2. And if we clean that up a bit, notice that the x squareds will end up canceling. The 2's will end up canceling. And so we're left with the 2xh plus h squared in the numerator. And then notice if we were to factor an h out in the numerator, okay, we could get the h that's in the denominator to cancel, so we're actually just left with 2x plus h. Okay, this probably doesn't mean much at the moment. I put this on here just kind of looking ahead a little bit, but to practice with function notation. All right, domain of a function. So there are different types of domains that you'll hear me refer to. So there's a function can have an implicit domain or has an implicit domain. And the implicit domain is just the largest possible domain for a particular function where you only exclude values, you only exclude real numbers that would give you imaginary outputs or that would make the function undefined. So maybe make the denominator of a function equal to 0. An explicit domain is a domain that is clearly stated and restricts the implicit domain. So this will happen often when a function models a real life situation. And let's say that like the input represents something like time. Time can't be negative. So in that case, the domain would need to be restricted. Like the equation that models, like let's say that it's a quadratic. So a quadratic has an implicit domain of all real numbers, but if that input represented something like time, well, time has to be greater than or equal to 0. So then the domain would be restricted, and you'll see it can be helpful if that's clearly stated. So let's practice stating the domains of these functions. So we're going to be stating the implicit domain of each of these functions. Okay, so this first function here, f of x equals to 4 over x squared minus 4. This is a rational function, right? It's a ratio of two polynomial functions. We know that we must exclude values from the domain that would make the function undefined. So we need to exclude values that would make the denominator equal to 0. So we know that x squared, let me switch colors for this one. We know that x squared minus 4 cannot be equal to 0. Okay, and there's different ways that we could solve for these values of x. You could probably even solve just using inspection, or I could factor. It's a difference of 2 squares. And I see that x cannot be equal to 2 or negative 2. So our domain, and I'm going to state the domain using interval notation. The domain would be all real numbers except for 2 and negative 2. So when I'm writing the domain in interval notation, I'm thinking about the real number line. And I'm going to exclude the values that are not part of the domain. So from negative infinity up to negative 2, but not including negative 2. So to exclude negative 2, I'm going to use the parenthesis, union, parenthesis again, and then negative 2. So we're kind of hopping over negative 2. And then up to 2, right, between negative 2 and 2, just not not including 2 or negative 2 are part of the domain. So use parenthesis union parenthesis 2 to exclude 2, and then to positive infinity. So that would be our domain using interval notation. Okay, for the function g of x equals to the square root of 2x plus 10, the square root, we know what's underneath the square root must be greater than or equal to 0. So 2x plus 10 must be greater than or equal to 0. And this is just a linear inequality, so we can think about subtracting 10 from each side and then divide by 2. So x must be greater than or equal to positive 5. X must be greater than or equal to negative 5. So I think about the number line and how I would represent that statement on the number line. Well, negative 5 is included. So to include negative 5 using interval notation, I use the bracket and then all the way to infinity. So comma, infinity. Remember with infinity, it's not a finite number, so we use a parenthesis. It just keeps going on and on and on. And then this last one, h of x equals to x divided by the square root of x squared plus 2x minus 3. Well, that is tricky, right? It's not a rational function, but it is a function that is a fraction, is a ratio. So we know that we can't have the denominator being equal to 0. But because we have that square root, whatever's under the square root is going to have to be positive. So to find the domain here, we could actually find the solution set to this inequality. And because this is a higher degree polynomial inequality, so polynomial inequalities that are a higher degree than 1, so linear inequalities, you can actually use properties of equality to help you get x by itself on one side of the inequality. But for higher degree polynomial inequalities, like a quadratic inequality, we need to do the analysis line. So I want to find the values that would actually make the left-hand side there equal to 0, because if there's going to be a sign change, so going from positive to negative, it's going to occur at the values of x where the left-hand side there is equal to 0. And that actually factors to be x plus 3 times x minus 1 on the left there. So negative 3 and 1 would make the left-hand side there equal to 0. So I put those values on the analysis line in order. So negative 3 and 1. And then I want to know what's happening to x squared plus 2x minus 3 to the left and right of each of those test values. So you can either think about the graph of x squared plus 2x minus 3. That's a parabola that opens up. So I know that the graph will go from being positive, right, to the left of negative 3. The y-coordinates for the points will be positive, and then it will dip below the x-axis, be negative, and then go back up again to be positive. Or you can use actual test points. So like you could substitute in negative 4, 0, 2 into either of these and see what values you get. Like if we substitute 0 in, well, then we would get negative 3, so negative values. Okay, so we're not done. We need to state this domain in interval notation. Okay, and we want all the values that would make this a true, either of these statements, true statements. Okay, so since the expression on the left would be positive or strictly greater than 0 to the left of negative 3, That would be negative infinity to negative 3. Negative 3 is not included though, because if you substitute in negative 3, we would get 0. We're saying that x squared plus 2x minus 3 must be strictly greater than 0. Okay, so then we'll use union. Between negative 3 and 1 is negative, so that would give us false statements if we plugged any values between negative 3 and 1 into that inequality. And then from 1 to infinity, those would give us positive values again, but not including 1, right? If we plugged in 1, we would get 0. So that negative infinity to negative 3, union 1 to positive infinity would be the domain of that function. Okay, range of a function. So the range of a function is the complete set of all possible resulting values, y values of the dependent variable, or the x values of the domain. To determine the range of a function, it's helpful. We're not really using algebra. It's helpful to think about the graph of the function, and in particular, the function's end behavior. And you're going to come up with some ways in calculus that will help you with determining the range of a function. Okay, it can be helpful to find the intercepts of a function. So I'm referring to the x-intercepts as well as the y-intercepts. X-intercepts, remember, you set y equal to 0 and solve for x. Y-intercepts, you set x equal to 0 and solve for y. And then remember to pay attention to what a question is asking for. So if you're being asked for the x and y intercepts, that usually means that you need to they're asking you for points, and you need to represent points as ordered pairs, so x comma y. Okay, so practicing locating the intercepts, the x and the y intercepts. And you need to be careful making sure that you're thinking about the domain. Okay, why don't we cut this in half? On the left here, I will do x. I will locate the x-intercepts. And then on the right, I will locate the y-intercepts. So for both of these functions, why don't we find the x-intercepts first? Okay, so that's setting y equal to 0. And then solving for x. So to solve for x here, we could square both sides of the equation. And then if we want to add x to both sides, we would get x equals to 2. Okay, so our x-intercept would be 2, 0. And just to check, if I plug 2 in for x, that would give me an output of 0. That's my x-intercept. And then for g of x is a rational function. So for finding, we would be setting g of x equals 0. So notice when we do that, really, we just care about where the numerator would be equal to 0, because you could think about multiplying both sides of the equation by x squared minus 9. But remember, if the numerator is equal to 0, as long as the denominator is not equal to 0 as well, that would simplify to be 0. Okay, so I can factor that. And I get -1 and -3, or -3. Okay, so we would actually have, it almost looks like we would have two different x-intercepts. The thing is, you need to pay attention to the domain. And notice if we plugged in -3 for x, that would make our denominator equal to 0. So it actually looks like if you remember, there would be a hole at x equals to -3. So -3 is not actually an x-intercept, only -1, 0. And then finding the y-intercepts is pretty straightforward. We'll just plug 0 in for x. So to find our y-intercepts, y-intercept, it's not a function if there's multiple y-intercepts. P of 0 would be the square root of 2. So 0 comma the square root of 2 would be our y-intercept for the function p. And then g of 0 it looks like that ends up simplifying to be negative 1/3. So 0 comma negative 1/3 would be our y-intercept for the function g. Okay, so these are the common types of functions that you guys should be familiar with that you studied in Algebra 2, Pre-Calc, and we're going to be working with these functions all year. So for each of those functions that are listed above, you should have an idea, be able to picture what their graphs look like, have an understanding of what their domain is or how to find it. And it would also be extremely helpful if you kind of knew what their end behavior looked like. So what's happening to the y coordinates as x is approaching positive or negative infinity. And we'll talk more about end behavior, especially with limits. Okay, so we're going to stop there. Composite functions will be in